Start scary chapter 5. But before we start chapter 5, we have some algebra skills that we need to review. So get back in your time machine. We're going to go back to our Algebra 1 and 2 class. We're just going to do a little bit of some algebra skill reviews. Okie dokie? Okay. First thing we're going to review is FOIL. What does FOIL stand for?
First inner outer left.
Except you spelled FIOL.
First outer left.
There you go. So this is just a set of instructions that describes to you how you multiply two quantities together. So first, y times y is, and then outer, y times 7 is 7y. Inner, 2 times y is, and last, 2 times 7 is. And then we just combine our like terms. Which ones are the like terms there? The 7y and 2y, which gives us ooh, scary. Okay, so that's foiled out. So what does foiling allow us to do? We've changed from a multiplication problem into an addition problem, right? Instead of having two things that were multiplied together, we now have three things that are being added together. Why don't you take a minute and try to FOIL the next one? We'll give you approximately 1 minute to do that, and then we'll go through it together. Should be pretty easy stuff right now. Okay. The firsts gave us 6b squared. The outer, negative 3b. The inner, 8b. And the last, negative 4. When we combine our like terms, we get 6b squared plus 5b minus 4. Is that what you guys got? Nice. Now, foiling, again, always works, but there are a couple of special multiplication patterns that we can use to shortcut our way through things. Those three special multiplication patterns is there's the perfect square, where you're adding, a perfect square where you're subtracting, and then the very popular difference of two squares. So if I'm looking at this first one, which of the three multiplication patterns can I use there? Yellow, green, or blue? Green. So that says here that my a is x and my b is 3. So I'm going to have x squared minus 2 times x times 3, 6x, plus 3 squared. Everybody's okay with how I did that? What's the advantage here over foiling? What I get to skip? The combining like terms step, right? Accomplishes the same goal, I just didn't have that extra step that I had to show, like we did above. Everybody's okay with that? Do I have to do it that way? No. Could I have just FOILed this? Yeah. What can't you do? What is never, ever, ever okay to do? Is distribute the exponent. That makes your math teacher cry. The property of distribution is very, very special. It only works for multiplication and division. No other operation you'll see can you distribute. Please don't ever do that. We'll give some angry eyebrows too, because it's not only sad, but it's also angry. How about number 4? Which multiplication pattern could we use here? Yellow, green, or blue? Blue! So again, my A is y, my B is 5. So this just turns into y squared minus 5 squared, which is 25. Which is quite nice, right? Let's look at number 5. Which one can I use there? Yellow, green, or blue? Green, yeah. So here's a little tricky. A is really this 2a, and B is 1. So when I use my factoring pattern over here, I have like 2a squared minus 2 times 2a times b plus b squared. I'm going to write it out so you guys can see what happened here. What's 2a squared? It would be like 2a times 2a, right? So 4a squared. Ooh, that's tricky because what's it look like is happening there? Looks like the exponents distributed, didn't they? But Mr. Gulick says you're never ever allowed to do that. What's different about this one than what we wrote up there in blue? Come on, guys. The operation in between the two things is multiplication as opposed to subtraction, right? I guess there. You guys see that? When we talk about distributing, we're talking about across addition or subtraction. The only operation that can distribute across addition and subtraction is multiplication and division. Exponents can be applied across multiplication and division. It's not really distributing, though, because it's not, when we say distributive, we're always talking about across multiplication, or addition and subtraction. Anyways, and then negative 2 times 2a times 1 is just negative 4a, and then 1 squared is 1. So I wrote out a little extra step there, just so I could show you guys that 2a squared is really 4a squared, right? You guys okay? What could have you still done? FOIL! right? Do you have to use these multiplication patterns? No. What is the point of them? Supposed to make things go faster. If they're not making it faster or easier, don't do it, right? Try 6 on your own. Give you guys about uno minuto. Give it a try. See what you get. Whew. Skulik has a sinus headache. Ever happened to you guys? Yeah. Who got 9z squared plus 24z plus 16? You all should have gotten that. Any questions on that so far? Is okay? Okay. What now? Factoring. Before we do this, though, let's take a little time out to review our factoring decision tree. Now, why is it going backwards? You know what? One note. Sometimes I just don't understand you. You're like an infinite sheet of paper. Why don't you let me go over farther? Okay. So factoring. What do we factor? What mathematical object do we primarily use factoring on? Give you a hint. It starts with the letter P. Polynomial. That's correct. So that's what we're going to kind of be starting. That's kind of like the input into our decision tree. We're going to factor a polynomial. What's the first thing we look for? A greatest common factor. What do I mean by greatest common factor? So if I have something like 2x squared plus 8x plus 8, notice that we can take a 2 out to start, and then we would just worry about factoring the quadratic piece that's left. That's what I mean by a greatest common factor. The 2 would have been the greatest common factor. Does that all look familiar? Just reviewing some vocab. All right. Now, what do we do next? Well, it depends on the number of terms. When you guys talked about factoring, you should have talked about it in situations where you have 2 terms, 3 terms, and 4 terms. When I say a term, what do I mean? So the things that are being added together in your polynomial. in that example we just looked at, that has 3 terms in it because there's 3 things added together. Does everybody recall that? We're okay with that vocab? So we're going to have 3 branches here with the number of terms. So we're going to start with 3 terms first. So the first thing we're going to check, if it's got 3 terms, is that it's in the quadratic form. If it's got 3 terms and it's not in the quadratic form, then there's nothing we know how to do. We're just going to stop. If the answer is yes, then we have to look at the next thing. The next thing we want to check is to see if the leading coefficient, I'm abbreviating that LC, is equal to 1. You remember what the leading coefficient is? We go back to this example of 2x squared plus 8x plus 8. What's the leading coefficient? 2. After I factor the greatest common factor of 2 out, what's the leading coefficient then? 1. Okay. Okay. If the leading coefficient is 1, we're going to just do the short factoring. That means that we're just going to look for the 2 numbers that multiply to give us and then add to give us. And then that'll take us straight to our factored form. We'll do examples of all these different little situations here in a moment. If the leading coefficient isn't 1, then we're going to have to do the long factoring. That's where we set up the same question, find the 2 numbers that multiply to give us something and add to give us something. But we have to set up a factor by grouping problem afterwards. I guess I should probably say, let's do this. Okay. Let's go build out this two-term branch then. So the first thing we're going to check, is it a difference of two squares? I abbreviate that phrase as DOTS, difference of two squares. If it's yes, then we need to check the factors down the two-term branch. Oh, you're back.
Yeah, that's right this time.
Oh, good. Alexis, looks like you got to get out of jail free card. If it's no, then we check something else. What else could happen if it was two terms? So it could be a sum of two cubes or a difference of two cubes. If it's not a difference of, or a sum or two of, or sum or difference of two cubes, at that point you would stop. There's nothing more that you would need to do. If it is, then we need to check the two-term factor down the two-term branch. Okay. And then the last branch we have is for four terms. There's only one option here. And that's factor by grouping. If the answer is no, then you just stop. There's nothing more that we can try to do right now. If the answer is yes, you'll do that factor by grouping, and then you'll check each factor down the two-term branch. So that's like our factoring decision tree for factoring polynomials algebraically. Whoa! That got pretty big, Mr. Kulik. It looks really confusing. It does, but it's not so bad. I just like having a visual for some of us. It makes like the process a little bit easier if you can kind of visualize like, okay, what do I do next? What do I do next? What do I do next? And it's like it always tells you what to do next. Let's just kind of do some little vocab review on the side here. So dots is the difference of two squares. That's the factoring pattern. A squared minus b squared equals a minus b times a plus b. Sum of two cubes a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Difference of two cubes, a cubed minus b cubed, is equal to a minus b times a squared plus ab plus b squared. And then let's just show some specific targeted examples of like doing some of this types of factoring then. And then we'll go back to the notes page that I started with where all the factoring techniques are all kind of mixed up in there. Everybody cool? Okay. So a difference of two squares example. X squared equals 81. How does that factor? Elise? Great. So you can view x squared as x squared, and 81 is 9 squared. So using our factoring pattern from above, that's just going to be x minus 9 times x plus 9. It doesn't matter which one's first, the plus or the minus either. But you do need one of each. Okay. Oops. Sum of two cubes factoring. Let's say we have x cubed plus 8. So I can think of x cubed, well, that's just x cubed. 8 is 2 cubed. Yeah, 8 is 2 times 2 times 2. So if I plug those then into my formula up above, I have a plus b, so x plus 2. And then x squared, or a squared, which is x squared, minus a times b, so 2 times x, plus b squared, so 2 squared, or 4. Everybody's okay how to use that one? Make this one a little bit sneakier. About 8x cubed minus 1. It's a difference of two cubes. How do I write 8x cubed as something cubed? That's 2x cubed. How to write 1 as something cubed? It's 1. Yeah, 1 cubed is still 1. So my a is 2x. and my b is 1. So I have a minus b, so 2x minus 1. Then I have a squared. What's 2x squared? We did this a minute ago. 4x squared, right? We did that just a few minutes ago. And then I have plus a times b, so that's just 2x, plus b squared. 1 squared is just 1. Oops, I mean 2a squared, 2x squared. So let's recall how we do a short factoring for a quadratic. So you need to find two numbers that multiply to give you -6, and then have to add to give us -1. What are those two numbers? 2 and -3. Excellent. So that takes us straight to our answer of being x plus 2 times x minus 3. Everybody okay there? So let's do a factor by grouping example. Okay, factor by grouping. Remember the very first thing we have to make sure we have before we can start a factor by grouping? Well, it's not a greatest common factor yet. So factor by grouping would be something we do before or after we've already taken a greatest common factor out. And if you look at this, there is no greatest common factor. Yeah. This symbol here in the middle needs to be addition. Right now, what is the symbol? How do I write it so it's an addition problem? No, I'm not going to take out a negative, you silly goose. I'm just going to write it as plus a negative instead of subtraction. Isn't that way easier? My little goose. Everybody's cool? All right. Now that we've done that, I'm going to make two groups. Notice the term is, or the technique is called factor by grouping. So I'm making a group plus another group. Everybody see that? In the first group, I'm going to look for a greatest common factor between 2x cubed and 4x squared. What is the greatest common factor between those? 2x squared. That's correct. When I factor that 2x squared out, what does 2x cubed become? x. And what does 4x squared become? 2. Then I'm going to copy the plus sign. I'm going to do the same thing now for negative 3x minus 6. What's the greatest common factor here? Negative 3. When I factor that negative 3 out, negative 3x becomes x, and the negative 6 becomes plus 2. Very good. Now, if factor by grouping is possible, those two groups need to be identical. Oh, they are! So, if I think about this as one thing, and this as another thing, do you see anything greatest common between those? The x plus 2's, right? The x plus 2's are in common to each one. So if I factor the x plus 2 off, what's going to be left? The 2x squared plus negative 3, or just 2x squared minus 3. Everybody okay there? You remember doing that? Okay. The last sub-skill in that factoring tree was the long factoring. Oh, shoot.
I just gotta save it and maybe I'll do it.
Okay. Notice this is the long factoring since the leading coefficient here is not 1. So remember how this one works. Two numbers that multiply to give us 12 times 6. And add to give us 17. What gives a multiply? What are the things that can... Okay, so this is one's a little bit harder than one that you usually can do in our head. What should we start with, the multiplication problem or the addition problem? Always the multiplication problem, because there's finitely many integers that can add or multiply to give us to 72. So what multiplies to give us 72? 1 and 72, negative 1 and negative 72. None of those work. 2 and 36, and then negative 2 and negative 36. Those don't work. 3 and 24, negative 3 and negative 24. Those don't work. 4 and 14, negative 4 and negative 14. Those don't work, although that's getting pretty close. 5 doesn't go into 72. 6 and 12 and -6 and -12. Again, that doesn't work. Okay, keep going. 7 doesn't go in. That's embarrassing. 8 and 9 go. And aha! That's the one. So what do I do with those two numbers now that I found them? It doesn't go straight to our answer. What I'm going to do with those two numbers is it's going to allow me to rewrite this as a 4-term quadratic.
Say what?
So I'm going to rewrite the 17x as 8x plus 9x. And now I'm just going to do my factor by grouping. What's the greatest common factor I can take between 12x squared and 8x? 4x, very good. That's going to leave me with 3x plus 2. And if I look at the second group, what's the greatest common factor between 9x and 6? 9x and 6? 3. Great. When I take the 3 out, what is left? 3x plus 2. Hey, look at that. It's almost like this was supposed to happen. If I factor the 3x plus 2 out, what am I left with? The 4x plus 3. Everybody's okay there? So that's a review of those 5 little or 6 little sub-factoring skills that make up the different factoring components of that big factoring diagram that we just wrote out. Okay? Let's go and take a look at some of these random factoring problems and apply what we have just reviewed to these specific problems. Okie doke. Now, some of them, it'll be like overkill, but with what we just did. But I wanted to do it like the right way from the beginning. Let's look at number 7 first. First thing we check for down the factoring diagram is greatest common factor. So greatest common factor for number 7. No. Great. Okay, continuing on. Next thing we do is we look at the number of terms. How many terms are there for 7? 3. So we go down to the 3-term branch. Is it in the quadratic form? Sure, it's something squared plus something x plus a constant. Of course it is. Is the leading coefficient 1? Yeah, of course it is. So we should just be able to do the short factor. Come on. Come on, you stupid thing. Okay. So to do the short factor here, we need to find 2 things that multiply to give us 4, and then add to give us 4. What are those 2 things? 2 and 2. So how does this factor? X plus 2 times x plus 2. And then the directions on our tree tell us to check each of these factors down the two-term branch, right? Okay, so x plus 2, that's two terms. Is it a difference of two squares? Well, no, because it's not something squared, right? It's an x, not an x squared. Is it a sum or difference of two cubes? No, because it's just an x to the first, not an x cubed, right? So we're done. Yay. Let's look at 8. I'm not going to keep going back to the factoring tree every time I do this from here on out. Is that okay? I just wanted to show you, demonstrate you like how it's going to can track through and tell me what to do in case I get turned around in one of these problems. Okay. First step though. Great. Is there a greatest common factor here? Yes. What is it? 2. Okay, after we factor the 2 out, what do we have? 3 terms. What's the leading coefficient on the 3-termer? 1. So it's a short factoring problem. I need 2 numbers that multiply to give me negative 54, and then add to give me 3. What are those 2 numbers? Times tables, times tables. So we need to get the mad minute problems back out. Which, okay, 6 plus 9 is 15, not 3.
9 minus 9, 6 is 3.
So positive 9 and negative 6 is what you need. Good. So my answer can just be z plus 9 and then z minus 6. And I know I'm done because those are both linear terms, so obviously we can't factor any of those anymore. Okay, let's do number 9. Luke, are you having an allergic reaction or something? Okay. Okay, just asking. You're just very red. I'm just checking. I don't want you to die in class or something. Yeah, okay. As long as we're on the same page with that. Okay, number 9. First thing we check for is... Excellent. Is there a greatest common factor? No. Okay. How many terms do we have? 3. Is in the quadratic form? Yeah, it's quadratic. Is leading coefficient? Not 1. So this means we're having to do the long factoring. So we need 2 numbers that multiply to give us negative 24. That's 2 times negative 12. And then add to give us 5. What are those 2 numbers? Oh, it's so embarrassing. It's taking so long. 8 and negative 3. Very good. Now, does that take us straight to the answer? No! What it does tell us is how to break up the 8b. So that we can do factor by grouping. Remember that I have to have an addition sign between it. So even though I wrote it as plus a negative 3b instead of minus 3b. Okay, what's my greatest common factor from the first group? Or not to be. Ha ha ha. Shakespeare joke. That's a question, though, guys. Yes, Matt. Absolutely. And from the second group, I can take out a -3. I notice that I have a b plus 4 in common. So when I factor that out, what I'm left is 2b minus 3. Whoa! Is this feeling familiar? You spent a lot of time doing this last year, from my understanding. Hopefully this is a skill that comes back quickly. Do 10 by yourselves real quick. Give you 2 minutos. Probably shouldn't need much more than that. Mr. Gulick would say this is a 15-second problem, but I'm talking about number 10 that you can see on the board. Whew. Did you get it? Did you get y minus 10 times y plus 2?
Yeah.
Give yourself a pat on the back. Good job, self. Try number 11. Don't forget that crucial first step. How many of you guys forgot the 3a as the coefficient and just wrote a minus 8 times a plus 2? Oh, don't forget about those leading coefficients. They got to be there in your final answer. They don't go away, but you just leave them alone out front all by themselves. But you got to still have them at the end. Did I trick you? Look at 12. What do I do with this? Start it the same way. Greatest common factor? None. How many terms? 3. Is it in the quadratic form? Well, it's not quadratic per se, but it is in the quadratic form. Because see, if we think about y as the same thing as cosine x, this was really the same thing as factoring 3y squared plus 13y plus 10, right? That we can do. It is in the quadratic form. Sweet, dude. Multiplies to 30 and adds to give us 13. What is that? 10 and 3, guys. Come on. Make my groups. And I'll say I have the 3y plus 10 in common. When I factor that out, I have the y plus 1. So that's my answer, right? Wrong. What's wrong with it? I got to put the cosine x back. Was that sneaky? Maybe it was a little sneaky. But it wasn't bad, right? It's like, oh, I've seen that trick once. I could do that again. You see where this is going, though, right? Because now we're mixing trig and algebra together, and you're like, oh, no. It's a wonderful, wonderful thing, guys. Okay. Elise? Sure. Want to do these guys? I mean, all right, you don't want to, but let's do these ones anyways. I guess that's fair. I asked a stupid question. You should give me a stupid answer back. Do you want to do it? Come on now. All right. So, number 13. Gosh, really? Let's just skip that one. How about we go to 14? First thing we look for. Greatest common factor. Is there one? No. How many terms? 2. Is that a difference of 2 squares? Yes. So how does it factor? Right? Well, z squared is just z squared. And then what squared is 36? 6. Okay, so how does this factor? Not. Yeah, there you go. You get one of each and a difference of 2 squares. Let's do 17. What do we start with?
Take out a 3a.
Yes. What do I get when I do that?
A squared minus 9.
Great. That's okay. And what do you notice about a squared minus 9?
A minus 3.
Yeah. Okay, so a minus 3.
A plus 3.
Yes. What do you think? You guys did a lot. I heard you spent a lot of time doing this. Yeah, so I'm glad that we're pretty okay with it. That it stuck all right. All right, should we do 15 and 18? Why not? That's a great answer. Why not? All right. Greatest common factor? No. How many terms? 3. Quadratic form? Yeah, right? If I replace just cosine with y. That's quadratic. How does that one factor? Who can factor that? Y squared plus 6y plus 9. Yeah, so y plus 3 times y plus 3. Or if you want to be fancy about it, you can call it y plus 3 squared. Am I done? No, what should I have to do? Yeah, I got to put that cosine x back in. Make sure you put the x with it. Can you do 18? Try it on your own. Dos minutos. That's Spanish for 2 minutes, I think. I don't really know. I took like half a semester of middle school Spanish. So I've learned more Spanish by helping my daughter play computer games than I remember from middle school. I know my colors in Spanish. Most of them. I shouldn't say all of them. Should get sine x minus 6 squared? Or sine x minus 6 times sine x minus 6? That'd be okay too. Not wrong if you wrote it that way. What'd you guys think? Is this okay today? Feels pretty doable. For homework, I'd like you guys to work on worksheet 1, which is super exciting. It's got like 6 foiling problems and then like 10 more factoring problems. Ooh, so hard, Mr. Kulik. I know, but it'll be okay. You guys can do it. I trust you. Any questions?